What if the oldest light in the universe wasn't where it was supposed to be, or when it was supposed to be born? Welcome back, traveler. Tonight, we drift through science. Imagine a beam of ancient light, older than galaxies themselves, slipping across the dark like a memory that refuses to disappear. It moves softly through the void, fragile yet persistent, carrying whispers from a universe that had barely begun to breathe. And now James Webb has found traces of that impossible glow. You're here in a quiet corner of the night, resting inside your own stillness as the world outside falls gently away. Let your breath loosen, your posture soften, and allow the calm to settle around your thoughts like a warm, dark blanket. Nothing demands your attention, nothing presses against your mind. For now, you're simply floating, held by silence, carried by the soft hum of cosmic history unfolding at its own unhurried pace. This discovery matters because it bends the boundaries of what we thought was permanent. Light this ancient should be weak, stretched thin by the long journey through expanding space. And yet Webb found it bright, structured, and strangely confident. To make sense of that, we travel into a realm where physics turns lyrical, where space curves like gentle waves, and where time behaves less like a straight line and more like a vast, echoing chamber. The universe, in its quiet way, is telling a story older than imagination. If this kind of calm exploration helps you unwind, I'm quietly grateful if you choose to support this little corner of the cosmos, perhaps with a like, a subscribe, or simply by staying here a little longer. This space grows through softness, not urgency, through curiosity, not noise. Whatever you decide, the fact that you're here already brings a warm kind of meaning to this journey. And as we drift deeper into this impossible radiance, this ancient light that shouldn't exist and yet continues to glow with quiet defiance, something begins to unfold. A deeper pattern, a hidden thread, a clue left woven into the darkness itself, waiting for anyone patient enough to follow it into the next stretch of the night. There is a soft truth about the universe that becomes clearer the slower you breathe. Nothing in the cosmos is young, not really, and every photon you've ever seen has already lived a long and wandering life. The light around you, from city lamps, from stars, from silent galaxies drifting far beyond human sight, is always telling a story from the past. And when James Webb looks out into the deep sky, it doesn't just see brightness, it sees age, memory, and the faint echo of beginnings. When astronomers talk about ancient light, they're describing photons that have traveled for billions of years across expanding space, stretched into longer wavelengths as the universe grows around them. The further we look, the older the light becomes, until eventually we reach a time when the first stars were just beginning to flicker into existence. Webb can detect these distant wavelengths because its mirrors and instruments were designed to capture infrared light, the stretched, cooled remnants of the universe's earliest glow. Seen through a calmer lens, those early photons feel like embers drifting at the bottom of a cosmic ocean, each one carrying heat that has almost gone cold. Their glow is dim, softened by distance and time, like candlelight behind a veil of mist. When Webb collects them, it's as if the telescope is cupping its hands around a fragile flame, protecting it long enough for us to listen to what it has to say. And in that listening, something essential happens. You feel the scale of your own existence loosen. You realize you are part of a universe that remembers every moment, every breath of creation, even the ones we thought had vanished. In the quiet of this slow drifting, you start to understand that the cosmos isn't just expanding outward, it's expanding inward, opening space inside you for wonder. The strange thing is that this oldest light shouldn't look the way Webb found it. According to the models, the neat equations we trust to map our place in the cosmos, Early light should be faint, disorganized, and blurred by the turbulence of a young universe. Instead, the telescope found regions of brightness and structure that seemed too mature for their age, like newborn stars that somehow leap straight into adulthood, ignoring the sequence nature normally follows. When scientists study these signals, they analyze the wavelengths to decode their temperature, their distance, and the conditions of the early universe. Webb's sensitive instruments split the light like a quiet prism, revealing chemical fingerprints and thermal histories hidden within each photon. What they found, in several early galaxies and luminous patches, was far too complex for their expected timeline. It was like discovering footprints in sand that should have been untouched. Imagine walking into a forest just after dawn, expecting the silence of untouched paths, only to find fresh tracks curving between the trees. The air still cool, the leaves still damp, yet the evidence of movement is clear. Early galaxies detected by Webb feel exactly like those tracks, signs of formation and brightness where only calm darkness should have existed. And so a question rises from that forest floor of starlight. What does it mean when the universe behaves ahead of schedule? When the first cosmic structures appear earlier, brighter, and more confident than our theories allow? Perhaps the universe has always been more impatient than we thought, or perhaps time itself is more flexible than the rules we wrote for it. Light is not just illumination. It is a messenger carrying information about where it was born and what it has passed through. And the earliest light Webb captures moves through a universe that was still turbulent, filled with thick hydrogen fog, cooling plasma, and the first gravitational wells forming like gentle depressions in a soft fabric. In that environment, light should scatter easily, losing clarity before it ever reaches us. But Webb's images reveal shapes, real shapes, glowing through the haze of the early cosmos. These galaxies are brighter than models predict, hotter than expected, and far more organized. Their spectral signatures show star formation happening at speeds 10 or even 20 times faster than what the early universe should have allowed. It's as if nature was in a hurry, pushing itself into structure before the cosmic clock had even begun ticking properly. When you picture this visually, these early galaxies look like lanterns shining through a deep fog. The haze should swallow them, dimming their glow into a faint blur. Yet somehow their light cuts through, crisp and confident, like a lighthouse beam stretching across an ancient sea. The fog doesn't erase them, it frames them, making their brightness feel even more unlikely. And with that unlikely brightness, a deeper sense of mystery forms. If the universe was more efficient at creating structure than we thought, then everything, from galaxies to stars to planets to the atoms in your body, might have arisen from a faster, more energetic beginning. In a way, you are built from a universe that doesn't waste time. A universe that hurries toward former, even in its earliest breaths. Every deep field image Webb takes is like lifting a curtain that was closed for nearly 14 billion years. Behind that curtain lies evidence of star clusters, dust clouds, and gravitational interactions unfolding when the cosmos was less than 400 million years old. A mere toddler by cosmic standards. We expected flickers, but we found fireworks. The science behind this surprise comes down to luminosity, redshift, and mass. Galaxies this early should not have had enough time to accumulate the mass needed to shine so brightly. Redshift measurements confirm their age. They are not foreground objects masquerading as ancient ones. They are genuinely old, and the mass calculations suggest they are heavier than they have any right to be. Visually, think of these galaxies as stones skipping across a vast, expanding lake. Each skip is a burst of light. Each ripple is the trace of a gravitational event. But in Webb's early imagery, the stones seem to skip faster, leap farther, and leave ripples more intense than the calm waters of young spacetime should allow. And from this, a quiet thought emerges. Maybe the early universe wasn't calm at all. Maybe it was energetic, restless, and full of hidden mechanisms we haven't yet understood. Mechanisms that shape the cosmos with a confidence we never expected. The universe may be older than its light, wiser than its age, and more intricate than our predictions. Light this ancient carries the fingerprints of dark matter as well. It bends subtly, distorted by invisible mass clustered across billions of years. These distortions, gravitational lensing, let us see galaxies far behind the ones in the field of view. Webb often detects light amplified by these natural cosmic magnifying glasses, revealing structures we would never see otherwise. Through this bending of space, the distant glow becomes a kind of mural painted across warped geometry. The galaxies stretch like reflections in rippling water, their shapes elongated but still recognizable, their colors softened by time. The distortions don't erase their message, they make it richer, like hearing a familiar melody played on a slightly different instrument. And in those stretched reflections, a philosophical whisper lingers. The universe does not hide its secrets by burying them. It reveals them by bending them, twisting them into forms we might not expect, but can still recognize if we look closely enough. Understanding comes not from clarity alone, but from patience. Webb's discovery of overly bright ancient light hints at something deeper, that perhaps the early universe was seeded with more matter than we assumed, or that star formation processes were far more efficient. Some theories suggest exotic possibilities, like primordial black holes influencing early structure formation, or variations in the density of space-time itself right after the Big Bang. If you imagine this visually, it feels like watching the roots of a tree grow faster than the branches, stretching deep and strong long before the leaves ever appear. The early universe's roots, its mass distribution, its gravitational seeds, its invisible scaffolding, may have formed with a strength that allowed its later structures to rise more quickly. And from this view, a quiet realization surfaces. Everything you see today, and every galaxy, every constellation, every breath drawn under the night sky, may exist because the universe rushed into being with urgency, as if it couldn't wait to unfold its own story. The cosmos, in its first moments, may have been eager. As we follow Webb's findings, the question deepens. Why does this ancient light carry signs of maturity that contradict the expected timeline? Why do galaxies appear far more evolved than their age should allow? Why does the universe feel older than its own beginning? These questions form a thread, a quiet, shimmering path trailing off into the dark. And somewhere along that path, beyond the glow of impossible galaxies and the soft curve of expanding space, the next layer of the mystery begins to reveal itself, waiting with the same patient brightness as the ancient light that first caught Webb's attention. There is a moment when you stare long enough into the deep sky where the line between what you expect and what you discover begins to blur. The universe has a way of surprising even the most precise observers, leaving small cracks in our certainty through which wonder can quietly seep. These unexpected flashes of understanding often come not from what is bright and obvious, but from what is faint, distant, and strangely out of place. And the ancient light found by Webb belongs exactly to that category, a message written too early, glowing too strongly. To understand why this is so unusual, you need to picture how long it takes for structure to form in the young universe. The first stars didn't shine instantly after the Big Bang. They emerged from slow collapses of cooling gas, gathering into clumps under the gentle pull of gravity. This process should have taken hundreds of millions of years. Early galaxies, even primitive ones, required time to accumulate mass, form heavy elements, and ignite into brightness. Yet the galaxies Webb observed seem to have skipped these slow steps. glowing with a maturity that contradicts the expected timeline. In a gentler image, it's like stepping into a garden at dawn expecting to see only tiny sprouts, but instead finding strong vines curling up the trellis, blossoms already open, petals damp with early light. The soil is still cool, the morning barely begun, yet the growth appears weeks ahead of schedule. These early galaxies, with their unexpected brightness, feel exactly like those flowers, blooming too soon, yet undeniably real. And with that realization comes a quiet unease, the kind that invites deeper reflection. If the earlier structures grew more quickly than we thought, then the universe itself may not be the slow, measured storyteller we once imagined. It might be more like an artist sketching boldly onto a blank canvas, unafraid of speed, unafraid of imperfections, driven by some deeper, invisible rhythm we have yet to understand. One of the key puzzles here lies in the abundance of heavy elements seen in some of these early galaxies. Elements like carbon, oxygen, nitrogen, and iron require multiple generations of stars to exist. Stars that must first live, fuse lighter elements into heavier ones, and then die in brilliant explosions. These cycles take time, often billions of years. And yet Webb's instruments detect chemical signatures that suggest at least one full cycle of star birth and death had already occurred by the time these galaxies were formed. Scientifically, this implies extraordinarily rapid star formation rates, far higher than the calm models used to describe the early universe. Instead of stars forming quietly, slowly gathering gas over tens of millions of years, these galaxies seem to have experienced explosive bursts of creation. Their stars were born hotter, burned faster, and enriched their surroundings at a pace that feels almost impatient. The kind of cosmic evolution we expected to unfold gradually appears to have happened in fast forward. If you visualize this accelerated cycle, imagine watching clouds build into a storm not over hours, but in mere seconds. The sky darkens, the wind stirs, the first flash of lightning appears almost instantly. The atmosphere moves with a sense of urgency, as if time itself has thickened and sped up. These early galaxies move through their life cycles with that same condensed intensity, storms of formation erupting where only gentle breezes should have been. And from that image rises a quiet philosophical question. Why does nature rush in its earliest stages? Is there something about beginnings, whether cosmic, biological, or personal, that invites acceleration, as if creation itself prefers to gather momentum quickly before settling into calm? Maybe the earliest era of the universe was a moment of restless potential, a brief chapter where everything unfolded with a speed we are still trying to comprehend. Another layer of the mystery comes from the unexpected size of these early galaxies. Using gravitational lensing, astronomers can measure their mass and structure more accurately. In many cases, the galaxies detected by Webb are too large, far too large, for the time period in which they appear. Their mass suggests they had already accumulated enormous amounts of gas and dark matter shortly after the Big Bang. This contradicts the standard model of cosmic evolution, which predicts slow, gradual accumulation. The explanation might lie in the distribution of dark matter. Dark matter serves as the invisible scaffolding of the universe, providing gravitational wells where galaxies form. If the earliest patches of dark matter were denser or more irregular than we expected, they could have accelerated galaxy formation. These wells would act like deep valleys on a landscape, pulling gas and dust more quickly into their centers, allowing stars to ignite earlier and in greater numbers. To imagine this visually, think of raindrops sliding down smooth glass. If the surface is flat, the drops move slowly, They wander, merging only after long moments. But if the glass is tilted or shaped with grooves, the drops race down quickly, gathering into streams almost instantly. In the early universe, dark matter may have shaped the cosmic glass in such a way that everything flowed faster, gathering into bright islands of light long before we predicted. And in those bright islands, a subtle truth emerges. The universe doesn't always follow the paths we draw for it. It bends around assumptions, slips through expectations, and often behaves in ways that reveal how little of its story we truly understand. The earliest galaxies are not just scientific anomalies, they are reminders that knowledge itself must stay flexible. Another piece of the puzzle lies in the temperature of these early objects. Some of the light detected by Webb suggests the presence of extremely hot stars, massive, short-lived giants known as population 3 stars. These hypothetical first-generation stars would have burned intensely bright, producing ultraviolet radiation strong enough to reionize the surrounding hydrogen gas. Their existence has long been theorized, but never directly observed. If Webb's data hints at them, it would explain some of the unexpected brightness in the early universe. Population 3 stars, if they truly existed, would have shone like cosmic bonfires, lighting up the foggy universe and carving clearings in the thick hydrogen clouds. Their light would be fierce, sharp, almost metallic in its purity. And their deaths, rapid, violent, spectacular, would seed the cosmos with the first heavy elements, laying the foundation for all later chemistry, including the atoms that eventually formed you. This leads to a softer, introspective thought. Beginnings often require intensity. The first stars may have needed to burn harder so the later universe could breathe easier. In the same way, moments of transformation in our own lives sometimes arrive with an unexpected blaze, a sharp shift, a rapid change, a burst of clarity that reshapes the path ahead. Webb's discoveries also challenge our understanding of cosmic opacity. The early universe was filled with neutral hydrogen, which absorbs light easily. This should have prevented distant photons from traveling unimpeded. Yet Webb's infrared instruments capture clear images of stars and galaxies that should have been obscured by this ancient fog. Something pierced through that haze, either because the fog was thinner than we expected, or because early structures were powerful enough to carve holes in it. Visually, it resembles a lantern shining through thick smoke. The smoke should swallow the glow, dimming it into a faint smolder. But if the lantern is bright enough, or if the smoke has gaps created by previous bursts of flame, the light can escape more easily. In the early universe, radiation from forming stars may have carved tunnels through the fog, allowing photons to move freely. And this gives rise to a quiet idea. Even in the densest darkness, light eventually finds a path. The cosmos, with all its complexity, still follows a simple truth. Illumination spreads. It cuts through fog, bends around obstacles, reflects off distant surfaces, and continues its journey for billions of years, patient and unwavering. Some theories propose that the early universe may have expanded faster in certain regions, creating pockets where structure could form sooner. This idea, rooted in variations of inflation theory, suggests that space-time itself may have stretched unevenly, like fabric pulled more tightly in some places than others. These stretched regions could have cooled faster, allowing matter to collapse earlier. If you picture this physically, imagine a large sheet being tugged at several points. Some areas become thin, taut, ready to vibrate at the slightest touch. Others remain loose, slow to react. The early universe might have held similar textures, regions primed for rapid creation, others lagging behind. Webb's ancient light could be shining from one of those taut, accelerated places, and the reflection that follows is gentle but profound. Perhaps the universe is not uniform in its unfolding. Maybe its evolution mirrors the uneven rhythm of human experience. Stretches of calm punctuated by bursts of sudden growth, moments where everything shifts before we're ready. As astronomers sift through Webb's data, the patterns deepen. The oldest light shows unexpected structure, unexpected heat, unexpected maturity. It challenges the simplicity of our models and invites us into a more intricate story, one where the early universe dances between chaos and order, between turbulence and symmetry. And somewhere in that dance, as ancient light flickers across the vastness of cosmic time, another question begins forming quietly at the edge of understanding, a question that will pull us even deeper into the unfolding mystery waiting just ahead in the night. The deeper you wander into the universe's earliest light, the more you begin to sense that something subtle is at play, something that moves beneath equations, beneath predictions, beneath the tidy lines scientists draw to describe cosmic history. There is a trembling quality to this ancient radiance, a gentle insistence that hints at hidden layers we have not yet learned to see. It is as if the universe is nudging us, softly, telling us there is more to the beginning than we ever imagined. What James Webb detects is not just brightness, but structure. Delicate threads of matter arranged in ways that imply gravity was shaping the cosmos earlier than expected. Under standard cosmology, gravitational collapse moves slowly at first. Density contrasts need time to grow before they can pull gas into stars and galaxies. Yet the galaxies captured in these deep images show signs of having already undergone significant organization when the universe was still impossibly young. Their shapes defy the slow, steady timeline of classical models. To see this visually, imagine an enormous spider web shimmering in early morning light. The web should still be forming, threads half spun, the geometry incomplete. But instead, the strands are already taut, stretched across the air in perfect symmetry, dew gathering along their lines. The spider has worked faster than seems possible, its web capturing the dawn long before the sky fully brightens. These early galaxies feel like that, patterns woven too soon. And in that woven symmetry lies a philosophical whisper. Maybe the universe forms beauty faster than it forms explanations. Maybe pattern and elegance arise naturally, even in chaos, appearing long before we have the language to understand them. The cosmos may not wait for our theories to catch up, it simply unfolds. Another surprising feature of this early light is the presence of dust. Tiny, ancient grains forged in the hearts of dying stars. Dust requires time. It emerges from supernova explosions that scatter heavy elements into space. For Webb to detect dust-rich galaxies so early means that entire generations of stars must have lived and died within a cosmic heartbeat after the Big Bang. That timeline is astonishingly compressed, almost uncomfortably so. Scientifically, this suggests that the first stars, the massive hypothetical population 3 stars, must have burned extraordinarily bright and hot, fusing elements quickly before exploding with incredible force. Their violent deaths would have seeded the young universe with carbon, silicon, iron, and other building blocks needed for planets, life, and everything in between. This level of enrichment so early is one of the most striking signals Webb has revealed, requiring star formation rates far beyond traditional expectations. Visually, it's like watching sparks fly from a bonfire that ignites unexpectedly in the darkness. You expect only faint glows at first, tiny embers swirling slowly upward. Instead, the flames roar to life instantly, sending showers of sparks into the night. They scatter, drift, settle, and transform the surrounding landscape long before you thought any fire had taken hold. The early universe seems to burn with that same sudden brilliance. And from this brightness arises a deeper reflection. Perhaps creation is rarely gentle at the beginning. Maybe the earliest chapters of any story, cosmic or human, are marked by intensity, by fiery leaps, by overwhelming bursts of transformation. The universe may be reminding us that calmness often comes only after the first storms have passed. One of the most provocative puzzles lies in the smoothness of the cosmic microwave background, the leftover glow from the Big Bang. That faint radiation shows incredibly tiny variations in density across the early universe, suggesting a mostly uniform cosmos. And yet, the galaxies Webb has detected imply much stronger density contrasts than those early fluctuations would naturally produce. Something must have amplified structure formation in ways our models do not fully capture. The explanation may relate to dark matter, the invisible substance that shapes the universe through gravity. If dark matter clumped earlier or behaved slightly differently than expected, it could have accelerated the collapse of gas into early galaxies. Some theories propose that dark matter might have interacted with itself in subtle ways, forming dense filaments that acted as cosmic highways, guiding matter into early structures with surprising efficiency. To picture this, imagine a sheet of snow covering a frozen lake. At first glance, it seems uniform and untouched, but beneath the surface, invisible currents shape the movement of ice. Some areas crack earlier, others thicken, forming hidden pathways beneath the snow that guide the flow of water below. The early universe may have held similar invisible pathways, dark matter currents sculpting the roots of cosmic structure long before the first galaxies appeared. And in those hidden currents, a philosophical thought ripples quietly. The most important forces shaping our lives are often the ones we cannot see. Gravity, dark matter, memory, time, all of them exert influence without ever appearing directly, leaving patterns we feel long before we understand them. Another surprising clue comes from the ratio of ionized to neutral gas in the early universe. The process of reionization, where the first stars re-energized hydrogen atoms, was expected to be slow and patchy. But Webb's observations show pockets of ionized gas that suggest large regions were cleared of neutral hydrogen surprisingly early. This implies that the early stars were not only bright but numerous, their ultraviolet radiation strong enough to carve tunnels through the cosmic fog. Scientifically, this means reionization may have unfolded faster than predicted, driven by galaxies far more luminous and efficient than our models assumed. These galaxies acted like clusters of powerful lamps, illuminating the darkness and reshaping the surrounding medium at a pace that challenges standard theory. If you imagine this visually, the early universe looks like a foggy plain lit by sudden bursts of starlight. The fog should linger, thick and stubborn, yet instead it recedes in expanding circles, pushed back by clusters of brilliant flame. Darkness is transformed not gradually, but in swift, confident waves. And the reflection that follows is gentle but resonant. Even in a universe born from chaos, clarity can arrive faster than expected. Illumination does not always creep, sometimes it surges. Another clue comes from the gravitational interactions seen in these early structures. Some of the galaxies appear to be merging, a process that usually requires long timescales and significant gravitational influence. Mergers generate turbulence, trigger starbursts, and reshape galaxies dramatically. For Webb to observe merging galaxies so early means that the cosmic landscape was far more dynamic than we thought. Scientifically, this indicates that matter was not distributed evenly across space. Instead, it gathered quickly into clumps that interacted violently. enriching their environments and fostering accelerated growth. These interactions may have played a key role in the rapid formation of early brightness. In a softer image, these galaxies feel like dancers drawn toward each other in a vast, silent ballroom. They move slowly, gracefully, but inevitably. Their trajectories curve like gentle arcs, their motions guided by invisible threads. The dance begins much earlier than expected, reshaping the floor beneath them with each step. And from this dance emerges a quiet truth. The universe's story has always been collaborative. Nothing forms alone. Even the earliest galaxies grew through encounters, through shared motion, through gravitational conversations whispered across expanding space. Webb's revelations invite us to reconsider the nature of time itself. If early structures are older than they should be, then our understanding of cosmic timing may need recalibration. Time in the universe is not just a linear sequence. It is shaped by expansion, gravity, energy, and geometry. Slight changes in any of these elements can alter the rhythm of cosmic evolution dramatically. And as that rhythm unfolds in these early images, glowing, structured, impossible, another layer of the mystery calls softly from deeper within the ancient light, urging us forward into the next quiet revelation waiting just ahead in the dark. There comes a point when studying the oldest light, where distance stops feeling like a simple measurement. It becomes something stranger, something elastic, shifting, almost alive. You begin to sense that the farthest places in the universe aren't just distant in space, but distant in time, in temperature, in meaning. And as James Webb peers deeper into this ancient glow, distance itself begins to reveal its hidden complexity, showing that the cosmos may not be arranged the way we once believed. In physical terms, distance in an expanding universe is a moving target. The space between galaxies stretches continuously, carrying them away from each other even as their light moves toward us. When we say light has traveled for 13 billion years, we don't mean the source is 13 billion light-years away. Due to expansion, the real distance is far greater, often more than twice that number. This disconnect between travel time and present-day separation is one of the most mind-bending features of cosmology, and it lies at the heart of Webb's surprising discoveries. To visualize it gently, imagine a quiet river flowing beneath a thin layer of fog. A leaf falls onto the water upstream, drifting slowly toward you. By the time it arrives, the riverbank has shifted. The currents have widened the channel, and the distance between the point where it fell and the point where you stand has grown larger. The leaf's journey tells you one story. The river's expansion tells another. Light crossing the universe travels in the same quiet contradiction. And in that contradiction lingers a philosophical reminder. Not everything that reaches you comes from where you think, or when you think. The universe sends messages that stretch across changing landscapes, reshaped by forces you cannot see, carrying truths that require patience to understand. What makes Webb's ancient light so puzzling is that these early galaxies appear too close to each other for the era in which they formed. Their clustering suggests stronger gravitational attraction and denser regions of matter than conventional cosmology predicts. Early space should have been smoother, more uniform, less structured. Instead, the data shows pockets of matter pulled tightly together, as though gravity were working harder than expected, gathering building blocks at a pace that feels too quick for the universe's age. Scientifically, this implies that the initial density fluctuations, the tiny ripples in the early universe, were larger or more varied than measured in the cosmic microwave background. These ripples acted as seeds for galaxies, and their amplitude controls how fast matter collapses. If the seeds were deeper, the collapse would have accelerated, leading to earlier clustering. But the mismatch between the microwave background and Webb's observations suggests that something in our understanding of early density may be incomplete or oversimplified. Visually, it's like observing ripples spreading across a calm pond just after sunset. You expect them to be small, evenly spaced, gentle. But instead, you find some ripples much deeper, darker, and stronger than others, as though hidden stones beneath the surface have shaped the waves differently. Those unseen stones are like the early density variations, invisible influences sculpting the very first patterns long before light could reveal them. And this leads to a contemplative thought. Perhaps the universe's earliest blueprints weren't drawn as delicately as we imagined. Maybe the first lines were bold strokes, heavy marks made with confidence rather than caution, imprinting structure into the cosmos in ways that still echo across the night. Another clue appears when we study the redshift of these galaxies. Redshift measures how much the universe has stretched the light on its journey, and it correlates with distance and age. The galaxies detected by Webb have extremely high redshifts, placing them close to the cosmic dawn. Yet their physical sizes, brightness, and complexity resemble galaxies that should have formed much later. This mismatch challenges the timeline of structure formation. Scientifically, this tension suggests that star formation began sooner and more efficiently than our models allow. Gas cooled faster, gravity operated more aggressively, and feedback mechanisms, like supernova explosions and stellar winds, may have played different roles than expected. Some theories propose that exotic processes, such as interactions with dark energy or variable expansion rates, could modify early dynamics in ways we are only starting to imagine. In a softer image, think of the early universe as clay spinning on a potter's wheel. You expect the potter to start gently, shaping slow curves, forming the vessel gradually. But instead, the clay leaps upward quickly, taking shape before your eyes, rising into form with surprising speed. The potter's hands move with intention you didn't anticipate, sculpting the cosmos faster than the wheel should allow. And from that unexpected shaping comes a whisper of reflection. Beginnings often surprise even their creators. The universe may have been sculpted by forces that moved with urgency, as if eager to bring form out of formlessness. Another wrinkle emerges when considering the geometry of early space. Under Einstein's equations, the curvature of the universe depends on its total energy and matter content. Observations have long suggested a flat universe, a large-scale geometry with no overall curvature. But the early clustering seen by Webb might hint at regions where curvature fluctuated more strongly than assumed. These local variations could have accelerated the gathering of matter, enabling early galaxies to grow faster. Scientifically, this would mean the universe wasn't perfectly smooth from the start. Its geometry may have been slightly wrinkled, with subtle distortions that guided matter into pockets of early formation. These wrinkles could arise from quantum fluctuations stretched to cosmic scales during inflation, leaving behind gentle fingerprints in space-time. Visually, imagine a large sheet of fabric stretched tight in the wind. Even though it appears mostly flat, small creases form unpredictably, places where the fabric dips inward or rises outward. Dust blown onto the sheet gathers along those creases, collecting in patterns shaped not by the dust itself, but by the hidden geometry beneath it. Early galaxies followed similar creases, gathering where space bent deepest. And in those creases lies a philosophical echo. The shapes you see in life often reflect structures hidden beneath the surface. What appears random is sometimes guided by patterns too subtle to notice without stepping back or looking deeper. Another puzzle comes from the temperature of the cosmic background radiation at the time these galaxies formed. The young universe was warmer, meaning gas resisted collapse more strongly. Higher temperatures make it harder for matter to clump, slowing star formation. And yet Webb reveals galaxies that formed stars explosively, in conditions that should have been hostile to such rapid assembly. Scientifically, this contradiction implies that either cooling mechanisms were more efficient than we understood, or that additional forces helped compress matter despite the higher pressure. Possibilities include early black holes exerting gravitational influence, strong magnetic fields shaping flows of gas, or exotic particles altering cooling rates. Each possibility opens new avenues of inquiry into the physics of the early universe. To picture this, imagine trying to gather handfuls of warm sand. The grains slip through your fingers, refusing to settle into a solid shape. But if the sand cools quickly, or if the winds push it in your favor, you might form a small mound despite the difficulty. The early universe may have benefited from similar invisible winds, shaping matter despite heat that should have scattered it. And from that difficulty comes a contemplative insight. The most unlikely structures often form in environments that seem entirely unwelcoming. Complexity sometimes arises precisely because conditions are challenging, not in spite of them. As Webb continues to reveal these impossibly early galaxies, the tension grows between what we expect and what we observe. The ancient light stretches across billions of years, carrying a story that feels slightly out of order, as if the universe began writing its chapters faster than we can read them. Each new observation folds another layer into the mystery, inviting us to rethink what cosmic time, distance, and structure truly mean. And somewhere in that deepening story, glowing softly at the edges of comprehension, a new question begins to shimmer, calling us toward the next quiet revelation waiting deeper within the ancient dark. There is a moment when you contemplate the oldest light long enough, where curiosity deepens into something quieter, something closer to reverence. You begin to sense that the early universe wasn't merely chaotic or fast-moving, but strangely purposeful, as though guided by hidden rules that still hum beneath the surface of reality. The ancient light Webb captures feels less like an accident and more like a message wrapped in silence, repeating across billions of years with patient insistence. To understand the weight of this message, astronomers turn to the chemistry of early galaxies. The spectral signatures recorded by Webb show surprising quantities of oxygen, carbon, and silicon, elements far heavier than hydrogen or helium, which dominated the early cosmos. These heavy atoms form in supernova explosions, meaning entire generations of stars must have lived and died before these galaxies reached their observed brightness. This rapid enrichment challenges our models of star formation, requiring accelerated cycles that push the limits of known physics. Visually, it's like arriving at a freshly built house only to discover a fully grown orchard behind it. Trees mature enough to bear fruit, their roots deep and tangled, as if they had been growing for decades longer than the house itself has existed. The timeline feels impossible, yet the evidence stands quietly, unshakably before you. That orchard mirrors the heavy elements swirling through Webb's early galaxies. And from that orchard comes a philosophical whisper. Sometimes maturity arrives faster than expected, not because time moved differently, but because growth followed an unseen urgency. The cosmos may have felt a deep instinct to evolve quickly, shaping itself with a pace beyond our understanding. Another layer of mystery emerges when considering the brightness of these early galaxies. Their luminosity suggests star formation rates far beyond what ordinary gas physics should allow. Cooling mechanisms should have slowed the collapse of gas clouds, radiation pressure should have pushed material outward, and turbulent conditions should have limited how many stars could ignite simultaneously. Yet Webb observes galaxies burning with intensity, as if fueled by an inexhaustible reservoir of energy. Scientifically, one hypothesis suggests the presence of dense molecular clouds, far denser than previously assumed, that could collapse rapidly into clusters of giant stars. These stars, many times more massive than those in the modern universe, would burn hot and fast, producing massive amounts of ultraviolet light and enriching their surroundings quickly. Their short lifespans would lead to early supernovae, feeding the cycle and pushing the galaxy into a state of accelerated evolution. In a softer image, it resembles a wildfire sweeping across a dry forest under a sudden gust. Sparks ignite instantly, flames leap from tree to tree, and in a short span the entire landscape glows with fierce brightness. The fire burns fast, reshapes the terrain, and leaves behind fertile ash that seeds future growth. These early galaxies shine with that same wild brilliance, and within that brilliance lies a gentle lesson. Creation is not always a slow, careful unfolding. Sometimes the universe chooses speed, intensity, and transformation through fire. Sometimes the first steps are the most dramatic. Another strange clue comes from the shapes of these early galaxies. Many appear surprisingly smooth, lacking the irregular distortions typical of young, turbulent systems. In a universe so early, we would expect chaotic fragments, clumpy proto-galaxies struggling to gather form. Instead, Webb reveals structures that are compact, cohesive, and symmetrically bright. Their morphological calmness contradicts the violent conditions expected in the era they inhabit. Scientifically, this suggests that gravitational interactions may have been more finely tuned than we assumed. Dark matter may have provided deeper wells of stability, smoothing the collapse of gas. Alternatively, these galaxies may be the survivors of an even earlier, more chaotic phase, the remnants of several mergers that settled quickly into equilibrium. Their symmetry might be a sign not of youth, but of resilience. Visually, these galaxies resemble candles standing straight in a quiet room. The air around them is still, the flames steady, their glow bright but poised. Yet outside that room, storms may rage, winds may howl, and chaos may unfold. The calm of the flame does not reflect the calm of the world, only its persistence. The early galaxies captured by Webb feel like those candles, burning steadily against impossible odds. And in that steady light lies a philosophical echo. Harmony sometimes forms in the heart of disorder, not after it. It emerges from turbulence, shaped by forces that seem hostile to balance, yet somehow created anyway. Another intriguing thread appears when examining the sizes of these galaxies. Some are compact, extremely compact, with luminosity packed into volumes far smaller than typical modern galaxies. This compactness suggests intense gravitational binding, as though these early systems were squeezed tightly by forces eager to condense them. Such density would accelerate star formation dramatically, acting as a cosmic pressure cooker. Scientifically, this compactness indicates that early gas cooled rapidly into dense cores, possibly aided by molecular hydrogen and early dust grains. These dense cores could ignite starbursts far more efficiently than later galaxies, where gas is more diffuse. The combination of density, heat, and gravitational compression forms a perfect environment for rapid evolution. In a gentler metaphor, imagine a cluster of fireflies gathered tightly within a small glass jar. Instead of drifting freely through a field, they pulse together in a confined space, their collective glow brightening the jar far more intensely than if they were spread out. These early galaxies shine with that same condensed intensity, light trapped within tight boundaries, magnified by proximity. And from that jar of fireflies, comes a reflection. The most powerful forms of light often arise in small spaces where conditions are intense, focused, and ripe for transformation. The universe may have learned to shine by compressing its earliest flames. Another clue involves the apparent ages of stars in these galaxies. Spectral data suggests some stars were already several 100 million years old at the time we observe them. An impossibility if the galaxies formed only shortly before. This mismatch suggests either ages are misinterpreted or star formation began far earlier than the galaxy itself, perhaps in smaller precursors that later merged. Scientifically, this points toward hierarchical formation, small protogalactic fragments merging repeatedly, creating layered populations of stars. If early mergers were common, galaxies could appear older than their assembly time, carrying the fingerprints of earlier smaller structures that predate the galaxy's final form. Visually, it's like finding pages from older books bound inside a new cover. The book itself is recent, but its contents are drawn from earlier stories, written long before the final volume was assembled. The galaxy is young, but its stars carry older histories. And from that bound anthology arises a thought. Identity is often a collection of earlier chapters, inherited from moments that existed long before the present form. Galaxies, like people, can be young and ancient at the same time. These growing contradictions, brightness too high, stars too old, dust too abundant, geometry too stable, begin to paint a picture of a universe that rushed through its earliest transformations with a kind of fierce determination. The models we built to describe those early eras now feel slightly too clean, too cautious, too modest. Webb's revelations show a cosmos that moved boldly, shaping itself with speed and confidence long before we expected such maturity. And as you follow this trail of impossible starlight, another layer of the mystery glows softly at the edge of perception, inviting you into the next quiet revelation, waiting just beyond the horizon of understanding. There comes a moment, as you drift deeper into the story of ancient light, when you begin to realize that the universe's earliest chapters are far stranger than they appear on the surface. The more you look, the more the familiar rules loosen, revealing cracks through which the unknown quietly slips. In these cracks lie hints that the cosmos may hold layers of behavior we have yet to imagine, patterns woven beneath the obvious structure, guiding events with a subtle rhythm that has echoed since the dawn of time. The key to uncovering these hidden rhythms lies in the behavior of early star clusters. Webb has revealed clusters so tightly packed that the density challenges traditional astrophysics. These clusters contain enormous populations of massive stars born simultaneously, forming what astronomers call superstar clusters. Such clusters require extreme conditions: cold gas compressed rapidly, gravitational wells unusually deep, and turbulence unexpectedly low. Their existence in such an early epoch suggests that primordial environments were more finely tuned than previously believed. To see this visually, imagine a swarm of sparks igniting at the same instant within a single breath of wind. Instead of flickering individually across the dark, they burst into life together, forming a dense, shimmering sphere of light. Their glow overlaps, strengthens, and merges into a single, vibrant pulse. Early superstar clusters feel exactly like that, bursts of brilliance formed from improbable compression. And from that shared ignition arises a quiet reflection. Sometimes brilliance does not come from isolation, but from togetherness. Light intensifies when held in a crowd, when many small flames rise at once, shaping a glow far greater than their individual sparks. Another layer of mystery deepens when examining the gravitational signatures of these early galaxies. Some of them exhibit rotation curves, suggesting unexpectedly massive halos of dark matter. halos far denser and more compact than those found in modern galaxies. These dense halos would have accelerated the formation of stars and condensed gas with remarkable efficiency, allowing galaxies to grow large quickly. But their density is puzzling, hinting at dark matter behavior that might differ from standard models. Scientifically, this suggests the possibility of self-interacting dark matter, a variant of dark matter that collides or interacts with itself in subtle ways. If early dark matter had a degree of self-interaction, it could clump more densely, forming gravitational wells capable of breathing galaxies into existence far sooner. Such a model is still speculative, but Webb's data nudges the conversation in that direction. In a gentle metaphor, imagine a crowd moving through a vast hall. If every person ignores the others, the movement is slow and scattered. But if they subtly coordinate, even without speaking, they can cluster, forming groups that travel together with surprising speed. Early dark matter might have followed a similar dance, converging more efficiently to shape the first galaxies. And from that dance arises a philosophical whisper. Invisible cooperation often shapes reality more than visible effort. The unseen movements of countless small forces may guide the formation of the greatest structures. Another unexpected discovery comes from the infrared color signatures of early galaxies. Many exhibit red hues, indicating not just extreme distance, but a surprising amount of dust absorption. Dust should be scarce in such young systems, yet Webb detects it in abundance. Dust absorbs blue light and re-emits it at longer wavelengths, giving galaxies a warm, red glow. The presence of dust suggests rapid cycles of starburst and supernova, enriching space faster than theories allow. Scientifically, this points toward top-heavy initial mass functions, early star populations dominated by massive stars. These giants burn hot, fuse elements quickly, and explode violently, generating dust grains in great quantities. Their rapid deaths fill the early universe with the seeds of complexity, the elements that form planets, oceans, and eventually life. Visually, it resembles ashes drifting from the first campfires of creation. The flames burn quickly, their smoke rising into the night, carrying tiny particles that settle into new spaces, ready to shape whatever comes next. The dust of the early universe drifts just like that, soft, silent, and transformative. And from those drifting ashes comes a thought. Every structure we know, every atom in our bodies, began as the residue of earlier flames. The universe's brilliance is built from the remains of its own past light. Another clue appears in the observed temperatures of the early intergalactic medium. Webb's data suggests that some regions cooled more rapidly than predicted, allowing star formation to begin sooner. The rapid cooling could indicate interactions between ordinary matter and exotic particles, or perhaps enhanced radiative cooling mechanisms involving primordial molecules like H2 or HD. Such molecules may have played a greater role in early structure formation than current models assume. Scientifically, this cooling affects how gas collapses. Cooler gas collapses faster and more efficiently, forming stars in dense clouds. If molecular cooling advanced quickly, it could explain the sudden bursts of early luminosity. Yet the abundance of these molecules in the early universe is still debated, making their influence a tantalizing mystery. Visually, imagine hot steam rising from a pot. Under normal conditions, it cools slowly, but if a cold breeze sweeps through the room, the steam condenses rapidly, forming droplets that fall back down. In the early universe, some unknown breeze seems to have swept through, cooling gas more quickly than expected. And from that cooling comes a quiet realization. Transformation often requires the right temperature. the right softness of conditions, the right slowing of motion. Change does not always come from heat. Sometimes it comes from calm. Another dimension of the puzzle lies in early black holes. Webb has revealed active galactic nuclei, powered by feeding black holes, in galaxies that formed when the universe was less than 1 billion years old. These black holes appear too massive for their age, suggesting either exotic formation pathways or extremely rapid growth. Standard black hole growth through accretion should take much longer, making their early presence difficult to explain. Scientifically, several theories compete. Direct collapse black holes forming from massive primordial gas clouds, black holes born from supermassive population 3 stars, or enhanced accretion in dense, gas-rich environments. Each pathway implies a universe more dynamic and permissive of extreme processes than previously thought. To picture this, imagine a tree that should still be a sapling, yet somehow already holds a full-grown trunk and sprawling branches. It shouldn't be possible, yet it stands there, firm and undeniable. Early black holes feel like those trees, mature far too early, rooted in mysteries deeper than we expected. And from those ancient roots comes a philosophical murmur. Sometimes what grows fastest is not what begins largest, but what receives the right conditions at the right moment. The universe may have offered those moments freely in its youth. Another thread of mystery emerges in the unexpected uniformity of certain early structures. Despite forming in turbulent environments, some early galaxies exhibit remarkable symmetry, with smooth light profiles and balanced mass distribution. This contradicts expectations that early systems should be chaotic, irregular, and fragmented. Scientifically, this uniformity hints at stabilizing forces, possibly early feedback loops between radiation, gravity, and gas flow that encouraged orderly formation. It may suggest physics acting with surprising delicacy, shaping structures with a soft guiding hand despite violent conditions. Visually, it's like watching a potter's wheel spin clay. Even when hands move quickly, the vessel takes on smooth, symmetric form, guided by subtle adjustments. The early universe may have shaped its galaxies with that same intuitive grace. And within that grace lies a reflection. Beauty can emerge even when the hands of creation move swiftly. Speed does not erase elegance. Sometimes it produces it. All these clues, early dust, dense halos, ancient stars, rapid cooling, unexpected symmetry, point toward a universe that began with fervor, intensity, and purpose. The oldest light doesn't just illuminate early structures, it illuminates the limitations of our assumptions. It shows us that the cosmos is more capable, more creative, more surprising than we thought. And as you drift along this deepening trail of impossible radiance, another layer of the mystery begins to glow softly ahead. A quiet puzzle hiding deeper in the dark, waiting for the next step of this journey through ancient light. There is a strange quietness that settles over you as you follow the trail of ancient light deeper into the cosmic past. It's the kind of quiet that feels deliberate, as though the universe is letting you lean close enough to hear something it rarely repeats. By the time you reach the earliest glow detectable by Webb, that quietness becomes almost overwhelming, not empty, but full of secrets held beneath the surface of creation. You sense that the universe has been trying to tell this story for billions of years, waiting for someone patient enough to listen. One key clue comes from the surprising temperatures of the earliest stars. Webb's spectral readings indicate some stars burned at temperatures far exceeding typical stellar models. These hyper-hot giants would have emitted intense ultraviolet radiation, carving tunnels through the hydrogen fog that filled the young universe. Such powerful stars require extraordinary conditions: dense gas clouds, rapid collapse, and minimal fragmentation. Their existence suggests that the early cosmos favored extreme stellar birth, producing giants capable of transforming their environment on timescales that defy expectations. Visually, these stars resemble brilliant torches inside a vast cathedral of darkness. Their flames burn with searing intensity, casting sharp shadows against the fog, illuminating regions that should have remained hidden. Their light doesn't merely shine, it cuts, slices paths through the cosmic haze like beams from ancient lighthouses, guiding the earliest forms of matter into order. And in that cutting light lies a reflection. Sometimes illumination requires intensity, not softness. Sometimes the first steps toward clarity are harsh, bright, and overwhelming. The universe may have needed such ferocity in its earliest moments, so the calmer patterns we recognize today could emerge much later. Another layer of the mystery emerges from the presence of early ionized bubbles. Webb's images show that large regions of space became ionized far sooner than expected. This reionization process, where ultraviolet light stripped electrons from hydrogen, was supposed to unfold slowly, unevenly. But the data suggests enormous bubbles of ionized gas expanding rapidly, implying that star clusters and early galaxies produced far more ultraviolet radiation than standard models predict. Scientifically, these bubbles indicate that early cosmic structures worked collectively, their radiation blending into large-scale patterns that reshaped the universe's transparency. Instead of isolated pockets of light fighting against darkness, the early cosmos may have glowed with collaborative intensity, clearing vast pathways through the fog and accelerating the emergence of visibility. In metaphorical form, it resembles lanterns scattered across a dark valley. One lantern alone illuminates little, but 100 lanterns glowing together melt the shadows, revealing the contours of the land. These early galaxies were those lanterns, flickering at first, then joining into a gentle blaze that shifted the very nature of space. And from that landscape emerges a philosophical whisper. Transformation is often communal. Light becomes meaningful not just when it appears, but when it joins with others, creating space where clarity can grow. Another intriguing clue is found in the gravitational lensing patterns surrounding ancient galaxies. Some of Webb's deepest images show distortions too pronounced for the expected distribution of dark matter at that era. These distortions imply the existence of massive structures, galaxy clusters or dark matter concentrations, that should not yet have formed. For such structures to exist so early, matter must have collapsed into large-scale configurations far faster than predicted. Scientifically, this raises the possibility that dark matter behaved differently in the early universe, perhaps forming filaments and nodes more rapidly. Alternatively, early interactions between dark matter and baryonic matter could have accelerated structure formation. These unexplained distortions act like fingerprints left in soft clay, evidence that invisible hands shaped the young cosmos in ways we are only beginning to interpret. In a gentle metaphor, imagine footprints pressed into snow moments after a fresh snowfall. You expected pristine white silence, untouched and smooth, yet instead you find paths traced by someone who passed through long before you arrived. The snow is young, but the footprints are old. Webb's early lensing patterns feel exactly like that, marks left too soon. And in those quiet footprints lies a thought. Beginnings often carry traces of movements we never witnessed. The universe is full of early steps that occurred in darkness, shaping the paths we now follow without realizing who walked them first. Another clue comes from the internal turbulence of early gas clouds. According to standard theory, these clouds should have been highly chaotic, with violent motions preventing efficient star formation. Yet Webb's data shows surprisingly calm internal velocity patterns, regions where gas moved gently enough to collapse quickly. This calmness contradicts expectations, suggesting early structures may have been stabilized by forces we do not fully understand. Scientifically, this could involve magnetic fields threading through gas, aligning flows and reducing turbulence. Magnetic fields are notoriously difficult to detect in early cosmic environments, but their presence could explain the unexpected calm that allowed gas to collapse rapidly. If true, this would mean magnetism played a far more influential role in early galaxy formation than current models account for. Visually, it resembles watching fog drift over a still lake at dawn. Despite the cold air and vast open water, the fog moves with slow grace, settling into gentle patterns instead of swirling chaotically. Early gas clouds may have drifted with similar softness, their motions quietly orchestrated by hidden forces. And from that drifting softness comes a reflection. Tranquility is sometimes the greatest catalyst for creation. Even in environments shaped by fire and expansion, calm pockets can emerge, enabling delicate structures to grow. Another unexpected element of Webb's discoveries comes from the metallicity of early stars, their abundance of elements heavier than helium. These metals act as cooling agents, allowing gas clouds to cool and collapse faster. The surprising amount of metals observed suggests that the early universe was far more chemically active than expected, with supernovae enriching space quickly and thoroughly. Scientifically, this could imply that the first stars were extraordinarily massive, burning through their fuel quickly and producing metals at unprecedented rates. Their explosions would have sent shockwaves through the surrounding medium, compressing gas and triggering new waves of star formation. The cosmos may have moved in successive pulses: ignition, explosion, enrichment, collapse, repeating far faster than models allow. Visually, this resembles waves crashing against a rocky shore. Each wave breaks, retreats, and returns stronger, reshaping the coastline with its rhythm. The early universe may have built galaxies through similar cycles, energetic waves that sculpted space with each burst. And from that rhythm arises a gentle truth. Progress often arrives through cycles, not steady lines. Creation moves in pulses, each one carrying the memory of the one before. Another clue lies in the clustering of early galaxies. Webb shows groups of galaxies tightly bound together, forming protoclusters at a time when such large-scale structures should barely be emerging. These clusters reveal gravitational interactions that require significant mass and time, both difficult to reconcile with the universe's young age at the observed redshifts. Scientifically, this clustering might indicate early regions of enhanced density, cosmic hotspots where dark matter and gas gathered with unusual efficiency. These hotspots could have been seeded by quantum fluctuations stretched during inflation, creating pockets where structure formed faster than elsewhere. Such a scenario introduces an element of primordial variety into the universe's earliest architecture. Visually, these protoclusters resemble islands rising early from a receding tide, patches of land appearing long before the ocean has fully retreated. They stand as hints of future continents, forming ahead of schedule. And in those early islands lies a thought. Some structures are destined to emerge early, drawn into form by the invisible shape of their environment. The cosmos may favor certain locations for growth, long before growth seems possible. All these clues, early lensing, calm gas, hot stars, rapid enrichment, tight clusters, converge into a single theme. The early universe was not merely faster than expected, it was more orchestrated. Patterns emerged that feel almost intentional, shaped by forces that remain partly hidden. The oldest light shines not only with brightness but with purpose. And as that purpose glows deeper, another quiet piece of the mystery begins to stir in the shadows, inviting you further into the narrowing tunnel of cosmic time, where the next layer of ancient light waits to whisper what it has carried across the dark. There is a point in this journey, somewhere between the distant glow of impossible galaxies and the soft hum of expanding space, where wonder begins to blur into melancholy. The deeper you look into the universe's earliest light, the more you sense a quiet ache woven into it, a kind of cosmic nostalgia, as if the universe is mourning a version of itself that no longer exists. The oldest light doesn't only reveal how the cosmos grew, it reveals what it has lost along the way. Scientifically, the expansion of the universe means that the earliest structures we observe are now unimaginably far from us, carried away by the stretching of space. Galaxies that were once gravitationally near are now separated by millions of light years. Their light, frozen in time, shows them as they once were long before they drifted beyond our reach. We are not only looking backward, we are looking at things that no longer exist in the form we see. Their present selves are distant strangers we will never meet. Visually, it resembles finding an old photograph tucked inside a drawer, one that captures a moment you can never relive, a place that has changed, or a person who has long since grown into someone new. The universe keeps its memories with the same bittersweet tenderness. These ancient galaxies are snapshots of a time that has already slipped away. And from that realization comes a quiet thought. Everything we observe in the cosmos is tinged with absence. The universe shows us what it was, not what it is. Light is a form of longing, an echo traveling across time, trying to reach someone who wasn't there when it was born. Another layer of this melancholy emerges when considering how much has vanished from those early eras. Many of the stars captured in Webb's ancient light have already died. Some exploded as supernovae, others collapsed into black holes, still others faded into white dwarfs. Their brilliance lingers only in the photons finally reaching us. What we are studying is the afterimage of a universe that has already moved on. Scientifically, stars burn their fuel according to mass. Massive early stars lived short, violent lives, leaving behind only fragments, enriched gas, dust grains, and gravitational scars. None of them exist in their original form. The light Webb sees is a message written by ghosts, signatures of stars that no longer shine. Visually, it feels like hearing a distant melody carried on the wind. The musician is gone, the instrument silent, yet the notes drift toward you with haunting clarity, preserved by distance and time. The universe sings with echoes of its earliest songs in the same way. And from that melody comes a reflection. What we love most often comes to us after it has already passed. Beauty is not only in the presence of things, but in their persistence, their willingness to reach across time even after they've vanished. Another dimension of the melancholy lies in the fact that we will never witness these galaxies as they are today. Space expands so quickly that many of them are now beyond the cosmic horizon, a boundary beyond which light will never reach us. They continue to evolve, collide and change, but their future will never be visible to us. Their stories diverged from ours long ago. Scientifically, this cosmic horizon marks a limit imposed by accelerated expansion driven by dark energy. Regions of space recede faster than the speed of light due to expansion, making communication physically impossible. The universe isn't just big, it is actively separating us from parts of itself forever. In softer imagery, it resembles watching someone walk away down a long road until they vanish into the haze. Not because they stepped out of sight, but because the road itself stretches beneath their feet. They move forward, yet you remain frozen in place, unable to follow. And from that stretching horizon comes a gentle ache. Some distances are not meant to be crossed. The universe teaches this not with cruelty, but with inevitability. Not everything is ours to witness. Another element of this existential sadness comes from the realization that we are seeing the universe at many different ages simultaneously. The night sky is a tapestry woven from threads of mismatched time. Every star, every galaxy, every cluster exists in a different era. There is no single now in the cosmos. Time is fractured, stitched together through light that took different paths and lengths to reach us. Scientifically, this is a consequence of finite light speed and cosmic expansion. The farther we look, the older the light. A galaxy 1 billion light-years away shows us its adolescent years. 10 billion light-years away shows us its infancy. We live inside a sky of memories, not moments. Visually, it feels like reading a book where every page comes from a different chapter of the story. Some from the beginning, some from the middle, some from the end. Yet somehow together, they still form a coherent narrative, one the mind must piece together with quiet patience. And from that fragmented narrative emerges a thought. Time is not a single thread, but a tapestry. We exist among overlapping eras, part of a cosmic quilt stitched together by wandering light. Another clue to this melancholy is hidden in the nature of redshift itself. As the universe expands, it stretches light into longer wavelengths. The oldest light is stretched so far that it becomes nearly unrecognizable, stripped of its original color and energy. Even the photons themselves are tired, worn down by the long journey, losing strength with every billion years they travel. Scientifically, this loss of energy is described by cosmological redshift. As space expands, it stretches the waves of light, lowering their frequency and cooling them. It's not the photons that change, but the space they move through that reshapes them. By the time they reach Webb, they are shadows of their original selves. Visually, it's like a voice shouting across a vast canyon. The sound grows fainter, the words stretch, and eventually only a whisper reaches the other side. But even that whisper carries meaning, fragile and precious, and from that fragile whisper comes a soft truth. Endurance transforms everything. What survives a long journey is often worn and quiet, yet it holds more meaning precisely because it endured. Another melancholy layer appears when considering how much of the early universe we will never see. Some light never reached us because dense regions absorbed it. Some never formed because stars failed to ignite, and some faded long before they could travel the required billions of years. The universe is full of lost messages, stories that dissolved before finding a listener. Scientifically, early gas clouds were thick with neutral hydrogen that absorbed ultraviolet light. Many first-generation stars shone without leaving any visible trace. Their entire lives unfolded unseen, unrecorded, forgotten by the cosmos, except in the effects they left behind. Visually, it resembles writing a letter and releasing it into a storm. Some letters will reach their destinations. Others will be torn apart by wind and rain long before they can be read. And from those lost letters comes a thought. Not every moment is preserved. Not every story is told. And yet, the ones that survive feel even more miraculous for having made the journey. All these layers, the ghosts of dead stars, the unreachable galaxies, the fractured timeline, the fading photons, form a quiet truth about the cosmos. The universe is beautiful, not because it is eternal, but because it is fleeting. The oldest light bears the weight of everything that has come and gone, a gentle reminder of impermanence written across the fabric of space. And as you follow that fading glow deeper into the cosmic night, Another question begins to shimmer softly at the edge of awareness, a question that leads directly into the heart of the universe's longing, waiting quietly in the dark for whoever dares to listen next. There comes a point somewhere deep in the trail of impossible starlight when the mystery stops feeling like a puzzle to solve and starts feeling like a mirror. The universe's earliest glow becomes something you recognize, not because you've seen it before, but because it resembles the long, quiet ache of remembering something you thought you had forgotten. The oldest light does not simply illuminate the cosmos. It touches a place inside you that feels equally ancient, equally unfinished. Scientifically, this sense of incompleteness arises because the earliest eras of the universe are fundamentally inaccessible. No matter how powerful our telescopes become, there is a wall we cannot see beyond, the surface of last scattering, where the cosmic microwave background formed. Anything earlier remains hidden, veiled behind opaque plasma that no light can escape. Webb's discoveries press against that boundary, but they cannot penetrate it. The first moments of creation remain locked away, forever beyond observation. In a softer image, it resembles approaching the edge of a frozen lake at night. You can see the ice stretching into the distance, reflecting faint starlight, but beyond a certain point the fog thickens, swallowing everything. You sense depth behind it, shapes moving beneath the surface, but the veil will not lift. The world before that moment remains unreachable, and from that unreachable horizon comes a philosophical murmur. Some beginnings are not meant to be witnessed. The origin of everything, but the true first moment, might be something the universe protects, not out of secrecy, but out of tenderness. Another dimension of this melancholy emerges when considering the universe's accelerating expansion. The farther into the future we go, the more galaxies will slip beyond our cosmic horizon. This means that one day, much of the ancient light Webb sees will vanish from visibility forever. Our descendants, if humanity survives that long, will live under a night sky empty of distant galaxies. The universe will appear smaller, lonelier, quieter. Scientifically, this fate is driven by dark energy, the mysterious force pushing the universe apart at increasing speed. As expansion accelerates, regions of space recede faster than light can travel. Their photons can no longer bridge the growing distance. In the far future, only the nearest galaxies will remain visible, and the cosmic history Webb now reveals will become inaccessible. Visually, it feels like visiting an old library one last time before the doors are sealed. The shelves stand tall, filled with stories from ages long gone, but you know that soon the lights will dim and no one else will read these pages. The universe's archive is slowly closing, one volume at a time. And from that closing archive comes a reflection. Knowledge itself is impermanent. Even truths written in the fabric of space-time can fade beyond reach. Another source of existential ache comes from the way ancient light reveals not only the universe's youth, but its loneliness. The early cosmos was smaller, denser, more connected. Galaxies interacted frequently. Gas clouds collided and mingled. Light traveled shorter paths. Everything was closer. Now everything drifts apart, carried by silent expansion. The universe is aging into solitude. Scientifically, the average distance between galaxies increases over time. Clusters pull together, but space between clusters stretches with ever-growing emptiness. The earliest structures we see were part of a universe far more intimate than the one we inhabit. What Webb captures is a portrait of cosmic childhood, a time of closeness that will never return. Visually, it resembles a childhood photograph found decades later, a snapshot of a moment when everyone stood close together, smiling, without knowing how far life would pull them apart. The tenderness of the moment hurts precisely because distance has replaced that closeness. And within that tenderness lies a thought. Every stage of existence carries its own beauty, but no stage lasts. The universe teaches this in ways both grand and gentle. Another soft ache emerges when considering how much ancient light tells us about time. The universe is not timeless, it is aging. And like any aging thing, it carries its past inside it, in photons, in structures, in the quiet background radiation that hums everywhere. Webb's discoveries remind us that time is not a line we walk, but a tide we are carried by. A tide that began long before us and will continue long after. Scientifically, this is reflected in cosmic time dilation. Events in the early universe appear stretched when viewed from our perspective. A million years there passes like a long, slow breath here. Time itself moves differently across distance, twisted by expansion and gravitational curvature. We observe a universe that appears slow motion in its infancy. In metaphorical terms, it feels like watching an old film in which every movement is slightly softened, slowed, elongated, yet the softness makes every moment feel heavier, more emotional, more deliberate. The cosmos's earliest steps unfold with that same slow grace, and from that slow grace comes a philosophical whisper. The past is not gone, it is merely stretched, woven into the present like threads of an old tapestry. Another melancholy truth becomes clear as we consider the fate of these early galaxies. Many of them no longer exist in any recognizable form. They collided, merged, were torn apart by gravitational tides, or dissolved into larger structures. Their identities were temporary. The light we see is a snapshot of a moment that no longer has continuity. Scientifically, galaxy mergers are one of the primary drivers of cosmic evolution. Small galaxies merge into larger ones, clusters interact, chaotic dynamics erase earlier shapes. The universe is built on the destruction of earlier forms. The beauty Webb reveals is fragile, a fleeting configuration of matter that vanished eons ago. Visually, it resembles sand castles built near the shoreline. Each one is unique, delicate, meaningful, but the tide eventually rises, smoothing them away. All that remains is the memory of their shapes, like the light of early galaxies lingering long after their forms have dissolved. And from those dissolved shapes comes a gentle insight. Impermanence does not diminish meaning. Sometimes it deepens it. Another thread of melancholy lies in the realization that we are part of this cosmic story, not observers standing outside it. The atoms in our bodies were forged by the very processes revealed in Webb's ancient light. The universe's early ferocity, its rapid formation, its chaotic cycles, all of it is carried within us. We are built from the ashes of vanished stars, from galaxies that no longer exist, from dust older than our world. Scientifically, every element heavier than hydrogen in the human body was forged in stars or supernovae. The iron in your blood, the calcium in your bones, the carbon in every cell, all of it comes from long-dead giants that lived in eras far removed from our own. Webb's observations show these processes unfolding in their earliest forms. Visually, it resembles opening an old book and realizing the ink on the pages is made from the ashes of forgotten fires. You are reading a story written not just with words, but with the remnants of worlds. And from that realization comes a soft truth. To gaze at ancient light is to gaze at the history of yourself. All these threads, cosmic loneliness, unreachable horizons, fading signals, vanished galaxies, scattered memories, converge into a single emotional truth. The universe is beautiful because it is fragile. It is meaningful because it changes. It feels alive because it forgets as much as it remembers. And as you drift through this growing tide of cosmic melancholy, another layer of the mystery begins to glow softly ahead, guiding you into the next stretch of the journey, where the quiet truth of the universe finally begins to take shape in the deepest dark. There is a moment, as you drift to the very edge of the oldest light, when the mystery stops expanding outward and begins folding inward. Everything you've followed across billions of years, the impossible galaxies, the vanished stars, the unreachable horizons, starts to feel strangely intimate, as if the universe has been telling you a story not about itself, but about you. The ancient light becomes a kind of mirror, reflecting something deeply human, the desire to understand where we come from and why we are here at all. Scientifically, this turning point emerges when we consider what the oldest light implies about our models of reality. Webb's discoveries challenge assumptions about the timeline of cosmic evolution, the behavior of dark matter, the efficiency of early star formation, and even the geometry of space-time. If the early universe formed structure faster than predicted, then our equations, elegant as they are, may be incomplete. They may need new variables, new symmetries, or entirely new frameworks to explain what came before. Visually, it resembles a beautifully drawn map that you have trusted for years, only to discover a corner of the world that does not fit within its lines. The land is real, the map is wrong, and yet the map is not useless. It is simply unfinished, waiting for its missing pieces to be drawn not in inkbow, but in curiosity. And from that unfinished map comes a philosophical whisper. The more knowledge expands, the more humility grows with it. The unknown is not an enemy. It is the invitation the universe has been offering since the first light bloomed. Another layer of this inward reflection comes from the realization that the universe is not static. Everything changes. Everything evolves. Even the laws that govern reality may not have been fixed from the beginning. Some theories propose that certain constants, like the strength of gravity or the behavior of fundamental particles, may have been slightly different in the earliest moments. If so, the universe we observe today is only one version among countless possibilities. Scientifically, this idea appears in theories of varying constants and early universe symmetry breaking. The universe may have passed through phases where physics behaved differently, settling gradually into the rules we now experience. If early conditions allowed for faster structure formation, then Webb's findings become not contradictions, but clues about earlier phases of cosmic behavior. Visually, it is like watching ice crystallize on a window. At first, the patterns grow wild, branching unpredictably. Then, slowly, they settle into a familiar geometry. The early universe may have crystallized the laws of physics in a similar way, passing from wild patterns into stable ones. And within that crystallization resides a gentle truth. Order is not born fully formed. It grows from chaos, shaped by forces that move with subtlety and patience. Another strand of reflection comes from the realization that the universe is not only expanding, it is aging. Every photon Webb catches is a reminder that time flows relentlessly forward, carrying stars into death, galaxies into mergers, and structures into dissolution. Even the universe's brightness will eventually fade. In the distant future, star formation will cease, galaxies will dim, and light will grow scarce. We live in an age that is cosmically young, a bright moment in a long trajectory toward darkness. Scientifically, this fading is predicted by the second law of thermodynamics and models of cosmic heat death. Over trillions of years, usable energy will dissipate, the stars will go out, black holes will evaporate. The universe will become cold, quiet, and still. Webb's ancient light is a reminder not only of the universe's beginning, but also of its eventual silence. In softer imagery, it resembles watching the last embers of a fire glowing in the dark. They still radiate warmth, but you know the glow will not last forever. The universe is warming us with those embers now, the remnants of its brightest days. And from those embers comes a whispered truth. Impermanence is not a failure of existence, it is the essence of it. Another quiet ache emerges when considering how little of the universe we can ever see. Observational limits ensure that vast regions of space-time will remain forever hidden from us. Our instruments cannot capture all light. Our physics cannot pierce every veil. The universe is mostly dark, mostly silent, mostly unreachable. We see only the smallest fraction of its story, a faint sliver of its true expanse. Scientifically, this limitation arises from cosmic horizons, redshift dimming, and early universe opacity. Even with perfect instruments, we could never observe everything. Reality exceeds our senses by design. The earliest moments of the Big Bang will forever remain hidden, not because they lack evidence, but because they produce no light that can reach us. Visually, it is like exploring a vast ocean with only a lantern. It illuminates a shimmering circle around you, but beyond that circle lies depth without end. You hear the waves, feel the breeze, sense the immensity, but you cannot see it all. And from that lantern-lit ocean comes a thought. Knowledge does not remove mystery. It coexists with it, deepening rather than diminishing the wonder. Another dimension of this inward turn involves humanity's place in the cosmic timeline. Compared to the universe's age, our existence is astonishingly brief. Every human who has ever lived occupies a moment thinner than a whisper compared to cosmic time. The stars Webb observes have burned for billions of years. Our entire species has existed for a mere moment, and yet we are able to see them, to understand them, to ask why. Scientifically, this ability arises from the complexity of consciousness, itself shaped by countless cosmic processes that began in the earliest stars. The atoms in our brains were forged in ancient supernovae. The water in our cells contains hydrogen, older than the Milky Way. We are built from cosmic memory, and we return that memory to the universe by thinking, by wondering, by observing. Visually, it resembles a child standing beneath an ancient tree, a tree that sprouted long before they were born, that grew through storms and seasons they never witnessed. Yet the child understands the tree, feels connected to it, even though they share almost no time in common. And from that connection comes a philosophical truth. Meaning is not measured in duration. Even the briefest consciousness can bridge billions of years. Another emotional depth emerges from the realization that the oldest light carries not only knowledge, but intimacy. When Webb captures photons that began their journey near the dawn of time, it becomes the first thing to touch them in 13 billion years. Those photons traveled alone across expanding space, stretched and cooled by the cosmos itself, until they finally reached the mirror of a telescope built by beings who did not exist when the photons set out. Scientifically, each photon's journey is shaped by gravity, expansion, and time dilation. It curves around galaxies, threads through cosmic voids, and loses energy along the way, yet it survives, carrying a message across epochs that defy comprehension. When Webb detects it, the photon's journey ends, not in space, but in understanding. Visually, it feels like a message in a bottle floating across an endless ocean, traveling through storms and darkness until it reaches the hand of someone who can finally read it. The universe has been sending such messages since its earliest breaths. And from that fragile connection comes a quiet realization. We are not separate from the cosmos. We are its way of remembering itself. All these reflections on mystery, on time, on meaning, on impermanence, converge into a single emotional truth. The universe is vast enough to make us feel small, yet intimate enough to make us feel seen. The oldest light should not exist the way it does, and yet it shines, insisting on being witnessed. And as you drift through this final chamber of ancient radiance, another soft glow begins to rise, calling you gently toward the last stretch of the journey. The part where all these scattered threads begin to gather, quietly preparing to settle into the conclusion waiting just ahead in the quiet dark. There is a quiet moment at the end of every long cosmic journey when the oldest light seems to exhale. You've followed it across impossible distances, through vanished galaxies and forgotten stars, through regions where time stretches and bends like soft fabric. And now, as the glow fades into the calm of your own breath, you can feel the universe settling around you, not as something distant, but as something deeply familiar. The ancient light no longer feels strange. It feels like a memory you've carried without knowing. Everything you've seen tonight, the two bright galaxies, the impossible clusters, the vanished stars whose ghosts still shine, paints a picture of a universe far more urgent and alive in its beginning than we ever imagined. It didn't grow slowly or cautiously. It rushed forward, burning with intensity, forming structures faster than our theories predicted. And yet, in that urgency, there was elegance, a quiet orchestration beneath the chaos, guiding matter into patterns that would one day seed worlds, oceans, and breath. The melancholy woven through that ancient glow lingers even now. We've seen how much has been lost. Galaxies that no longer exist. Stars that died billions of years before our species formed. Signals stretched thin by the expansion of everything. But the sadness is gentle, like looking at a faded photograph and feeling grateful that the moment was captured at all. The oldest light reminds us that beauty is not defined by permanence, but by persistence, by the miracle of surviving long enough to be seen. And in following that light, you've stepped into a truth that lies at the heart of existence. The universe is not something you are separate from. Every atom in your body was forged in the same ancient fire that shaped the galaxies Webb now uncovers. The carbon in your breath, the iron in your blood, the calcium in your bones, all of it was born in stars that lived and died long before Earth existed. You carry the universe within you just as surely as the universe carries its history within the photons Webb detects. Even the strangeness of this discovery, the galaxies that shouldn't be there, the clusters too mature for their age, the dust too abundant too soon, invites a softer kind of gratitude. It reminds us that the cosmos still has surprises left. For all our equations, all our instruments, all our theories, reality is still larger than our explanations. Mystery is not a flaw in our understanding. It is the invitation that keeps us moving forward, asking questions, looking up, drifting deeper. And as you let your breath settle into a slower rhythm, the night around you begins to feel different, not empty but full of stories carried across billions of years, full of old light that took the longest road imaginable just to reach your quiet corner of the world. Full of possibilities you haven't discovered yet, and questions waiting patiently in the dark. The universe is vast, but you are woven into it with the same quiet intention as any star. If this journey through ancient light brought you a moment of peace or wonder, I'm deeply grateful you shared it here tonight. And if you ever feel like drifting through another quiet corner of science, a gentle like or subscribe helps others find their way into this calm too. If you'd like, tell me in the comments where you're watching from and what time it is. I always love seeing how far these quiet stories travel. And now, As the glow of that oldest light fades softly behind you, you remain here, warm, safe, unhurried, wrapped in the slow breath of a universe that has been unfolding for nearly 14 billion years. You carry its memories in your cells and its curiosity in your mind. You are made of the very same stardust that once illuminated the early dark. And as the night settles fully around you, know this. The universe may be ancient, but tonight it feels closer than ever, not in distance, but in belonging.